So the answer is that this is always the case. Now, how do you prove something about sets? How do you prove that two sets are equal? Well, we need to show that the eigenvalues of A form a subset of the eigenvalues of A00 union the eigenvalues of A11, and then we need to show that the eigenvalues of A00 union the eigenvalues of A11 are a subset of the eigenvalues of A. If that's the case, then the two sets are equal. So typically we prove it one way first, and then we prove it the other way. So let's start by showing that any eigenvalue of A is either an eigenvalue of A00 or an eigenvalue of A11. That's what the union means. So how do we do that? Well, we pick an arbitrary eigenvalue of A, and we know that then there is an x such that A times x is equal to lambda x, and that vector x is not the zero vector. That's the definition of lambda being an eigenvalue. So we partition x into x0 and x1, where the sizes of these vectors match the appropriate sizes of the submatrices. So then we know that Ax is equal to lambda x. And if we then multiply this out, we get this right here. We do this times that plus this times that, that's this. And then this times that is that. And then here we multiply lambda times the separate subvectors. Okay, so now things get a little trickier. What we now notice is that A11 times x1 is equal to lambda times x1. Well, if x1 is not 0, not the zero vector, then that means that x1 is an eigenvector of A11 corresponding to lambda. So what that means is that lambda is indeed an element of the set of eigenvalues of A11. Now, if x1 is equal to 0, then we notice that this top part right here boils down to A00 times x0 is equal to lambda times x0. But that means that x0 is an eigenvalue associated with lambda for A00. So that means that lambda is an element of the eigenvalues of A00. Of course, it could be that both x0 and x1 are the zero vector, but actually that can't be, because then x would have been the zero vector. So what this shows is that lambda is either an element in the set of eigenvalues of A11 or an element in the set of eigenvalues of A00. So then we want to prove it the other way around. So now we want to show that the set of all eigenvalues of A00 union the eigenvalues of A11 is actually a subset of the eigenvalues of A. And we do that in exactly the same way. We pick an element in the set of eigenvalues of A00 union A11. And then we say, well, either lambda is in the set of eigenvalues of A00, or it is an element in the set of eigenvalues of A11. So here we pick the first case. If that's the case, then we know that there's a non-zero vector that satisfies this. Then we know that this is equal to that where we just pad it with zero vectors. But this is exactly this matrix times this vector. And notice that that's equal to this. And then we can pull the lambda out. So what we've just constructed is a non-zero vector such that A times x is equal to lambda times x. Now, similarly, we can say, what if it's not an eigenvalue of A00? Well, then two things happen. First of all, it is an eigenvalue of A11, so this must be true for some non-zero vector x1. But it's also the case that A00 minus lambda A must be non-singular, because if this here is singular, then lambda would have been an eigenvalue of A00. This time we try to find a vector in the null space of A minus lambda I, which is written on the left here. And it turns out that this vector here is constructed in such a way that if you multiply it out, you get the 0 vector. Now notice that this vector is well defined because we know that x1 exists. That comes from the fact that lambda is an eigenvalue of a11. And we know that this inverse here exists, and therefore this entire subvector here exists. So this is all well defined. So here is a theorem, and the theorem is just a natural extension of what we just looked at. If you partition your matrix in such a way that all of the matrices on the diagonal are square matrices, then you get what is called a block upper triangular matrix. And then the set of all eigenvalues of A is simply the union of the set of eigenvalues of the individual blocks on the diagonal. So here's another homework. What this homework asks is, if A is a symmetric matrix, which of course means it's square, and we have two eigenvalues that are not equal to each other, and we have corresponding eigenvectors xi and xj, then what this here asks is it the case that these two vectors are orthogonal to each other? So before you go and prove or disprove this claim, let's visualize the eigenvectors of a symmetric matrix. So here we have a symmetric matrix, 3, 1, 1, minus 1. And I claim that x0 and x1 here in this picture are the eigenvectors. So let's see what happens. X starts moving around. When x points in the opposite direction of x0, which is an eigenvector, a times x points in the direction of x0. So indeed, a times x is some constant times x. And then when x points in the direction of x1, a times x again points in the same direction. So here we have two eigenvectors. Now, if you look at x0 and x1, kind of eyeballing it, they kind of look perpendicular to each other. The fact that they look perpendicular to each other doesn't mean they are perpendicular, nor does it mean that for every symmetric matrix they are perpendicular, and therefore you're going to have to prove this one way or the other. Go do the homework. See me in the next video.